of sampling distributions for means and sampling distribution of proportions, right? Okay. Today we're going to count, let's say I take a random sample of 5 people. Like, I don't know. I got 5 people right here. They all said yes, by the way. They agree with the statement. Yeah? Okay. So, are you guys with me that the minute I did that, each of their responses was categorical. Yes, no, yes, no. In this case, all yeses. Yeah? Okay? All right. So, we had 5 people. If it's drawn randomly, each of them has a 40% chance. And the number that I find interesting, I'm summarizing each of their responses by saying 5 out of 5 people said yes, right? Or 5 people said yes. What kind of variable is this right now? This is binomial. We have a set number of trials, right? You either agree or you disagree. Everybody with me? Okay. So, knowing that this is binomial, could we find the probability that 0 people said yes, that 1 person says yes, 2 people, 3 people, etc.? Okay, so here's what I'd like you guys to do. Everybody pick one. Like, help me fill in this table. So, pull out your calculators, you're going to do binom. Which one would we use if I'm trying to find each individual one? Binom PDF. If you have an answer, just tell me how many agrees and then what the probability is. 0.23 what?
0.2304.
So 230, great.
0 is 0.07, 7 or 7.8.
I think it rounds up, yeah.
1 is 0.259.
2 is 0.34.
3, 4.
5, 6.
So 3, 4, 6. Okay.
5 is 0.010. 4 is 0.077.
7, 8.
Oh, mine says 7.6.
Okay. 7, 6, 8. Okay. Great. All right. How we doing? Everybody good? Could we find the mean and the standard deviation of this? Do we have to plug these into our calculator? We have formulas for the mean of a binomial. We have formulas for the standard deviation of a binomial. You guys can double check my arithmetic. I'm not very good with numbers.
I think the mean is 1.2.
No, the mean.
I got 1.09.
The mean.
Oh, the mean I got.
The mean should be n times p, not n.
No, the standard deviation.
Don't forget the square root.
Oh, yes.
Are we good? You guys. I'd like to take a deeper dive into this possible outcome right here. Is everybody with me? Can we? This was one person that said they agreed, yes? 1 out of 5. Could I turn that one person into a p hat?
Yes.
Yeah, how would I do that?
1 out of 5.
I would divide by 5, yeah? Could I turn these 2 people into a p hat?
Make samples from a sample.
What would I do to turn these 2 people into a p hat?
Divide by 5.
I would say 2 out of 5. What about this one? Can I turn them into a p hat? 3 out of 5.
4.
Are you guys with me that I could turn this whole set of successes into p hats by dividing by my sample size, in this case 5? Is everybody with me?
Wait, they didn't change both. Save it.
Not just is it going to change both, how is my mean going to change if I divide my entire distribution
It's gonna divide by
by 5? The mean's going to get divided by 5. You guys, are we comfortable with saying any binomial can be turned into a p hat by dividing by the sample size? Are we seeing this? Okay? So if I took the mean of this binomial and divided it by the sample size, what is the mean of my p hats going to be? What is np divided by n always going to work out to be? P, which in this case is 0.4, 2/5. Wait a minute. Hold on. If the mean of the p hats is always just going to be p, doesn't that mean p hat is always an unbiased estimator? Is everybody good? Sweet. And my standard deviation of my p hats
What else can I
would look kind of like this, but I don't know about you guys, but I don't like the way this looks. This looks really messy. And in fact, if this were an algebra class, we would not be allowed to leave like 2 n's in a fraction. We would be expected to simplify them in some way, yes? Do you guys trust my algebra skills? Great, perfect, you should. I've been doing it for a long time. So, what we have just found are 2 formulas to help us always find the mean and the standard deviation of the p hats. Now, looking at your formula sheet, do I give you these formulas? Those of you who are saying no, turn the page.
Yeah.
Okay?
I didn't see it, so my guess would be no.
I thought that was like close.
There's a whole other page to your formula sheet with this, all the formulas. Okay. So when we,
Standard error.
now, you guys remember how we said yesterday what happens if we increase our sample size? Our distributions become less spread out. Is everybody with me? How do we measure spread? What are our measures of spread?
Range.
Range. What else?
Standard deviation.
Standard deviation. You guys, can we see mathematically what happens if I use bigger numbers for n? I get bigger numbers in the bottom of my fraction, yes? If I divide by bigger numbers,
Small.
smaller overall. So mathematically, can we see it? Everybody good? Physically, can we see it? In terms of what we actually accomplished. Great. All right, lovely. All right, so now that we have formulas for mean and standard deviation, and we know what are the 3 characteristics we care the most about with every distribution, when we look at something, we want to analyze for 3 separate things. They are shape, center, spread. If we have the mean and we have the standard deviation, we have 2 of the 3, yes? So all we have left to do is talk about shape. And to talk about that shape, I want to start over here. What was the shape of this one?
Right. Screw right.
Skew to the right, yeah?
I forgot.
What was the shape of this one? It's starting to look normal. It's definitely getting closer to normal, yeah? Why was this one skewed right? Like if we had to put into words, which by the way is a way more complex question
It's not
than it sounds.
There were
off the
fewer.
chance that it's over there.
There were fewer. The sample size was smaller than the sample size below it, so there was less. There was more
So-
variation.
When we talked about the central limit theorem last week, we said larger sample size means sampling distributions get closer to normal. Are we seeing that here?
Yes.
This is definitely closer to normal than this one. This was definitely skewed right. And this was skewed right because basically these ones, yeah? And having a sample of 5, it's not that crazy to get a 0.6. It would have been pretty crazy with a sample size of 10. Okay. Now, let's look at this one real quick. If I asked you guys, could we draw or approximate a histogram of this distribution? Of these p-hats? We have all those relative frequencies, right? And as I look at this looks mostly symmetric except for this one little guy over here, yeah? Is everybody with me? So this one is kind of close to normal. Like when I look at this, I kind of see it's not normal, but it's close, yeah? How come this one didn't have the wackiness and shape that this one had? Both of them were sample size 5.
Every sample is different.
Okay, what else? What was my P of this one? Most likely. What do you guys think the percent of the bag was? 0.2 bag. We would expect a quarter of them to be pink. There were 4 possible colors, right? Okay. This one P was 0.4. So here's the deal. If I want you guys to think about P and 1 minus P. Here we have 0.4 and 0.6. They're kind of close to each other, right? 40% is pretty darn close. What would it be if they were perfectly the same? It'd be 50-50, yeah? Here we have 0.25, and then the opposite would be 0.75. They're further away from each other. Is everybody good? Okay. So P1 minus P and sample size all help us determine shape. So the shapes will be more extreme when P and 1 minus P are very extreme from each other. They will be more symmetric when P and 1 minus P are about the same. Everybody good? All right, so long story short, the distribution of P hat will be approximately normal if, big if, NP and 1 minus P are going to be greater than or equal to 10. Yes, I will expect you to memorize that. No, you shouldn't stress about that memorization. By the time we get through this, you will know it. I promise. So, every time we get a description of taking a sample, we want to kind of keep this as our frame of reference of where does our sample fit within everything else? Where does our sample fit within where possible samples could, what other possible samples I could take? All right. Now, I know you feel like your packet has a lot in it. I did a bad job. We can erase. Don't even worry about this part because it is restating literally everything we just said. Okay? There's one thing I do want us to know. When we talk about a distribution or like a dot plot or a histogram, okay? Like this is an approximation of a sampling distribution of P hat. What is my variable here?
Something and not something.
I'm sorry?
Like binomial.
Nope. More specific. It was the sample proportions though. So any sampling distribution of P hat, the variable is P hat. You had this P hat, someone else had this one, this one, this one. We all got different P hats. That's where we varied, yeah? Okay. Let's look at some examples here. Any of you guys like to watch videos that have cats or dogs in them? Sometimes? Anytime I'm like cranky, I watch a dog video and I'm usually in better mood right afterwards. All right. Suppose 90% of young adult internet users like to watch cat or dog videos. Suppose that a sample contacts 1,000 young adults and calculates p hat, the proportion in the sample who like to watch said videos. Okay. Tell me something I know just from reading that opening blurb. Mm-mm. P is equal to 0.9.
I just wrote that. I wrote what P is. That's why.
Is n equal to 1,000?
N is equal to 1,000. Lovely. All right. You guys, will this sample of 1,000 people have 900 who watch these videos? Could it? Could it be 902? Could it be 873? Okay, good. We're all on the same page here. So the variable is what we actually get in the sample. Great. What is the mean of all those samples going to be? Nah. Because what are we measuring from our sample? P hats. So the mean is going to be 0.9. If I ask what is the mean number of people in each sample, each possible sample, we're asking the mean proportion. So we would keep it as the 0.9. What is the standard deviation of the possible p hats we could get? What should I do? P, 1 minus P, all divided by N. Take the square root. Will it be normal? Real quick reminder, NP, the way you check for normality is that you check that for both NP and N1 minus P, they're both greater than or equal to 10. Always 10. Are those greater than or equal to 10?
Yes.
So it will be approximately normal. You guys, what would we expect to happen if our sample size was 9,000 instead of 1,000? Okay, so in terms of, would it still be normal, do you think?
Yes.
In fact, because the higher sample size is going to make these numbers bigger, not smaller, right? Will the mean change? So when you say they get closer, first of all, and look, I actually don't even remember if you used this phrase, but I'm going to be very picky about phrasing real quick. So if you're worried about remembering picky phrasing, here's a place to tune in. The p hats will get closer instead of using the word they.
Yeah.
Okay? we are getting to a place where your language is going to become imperative, okay? Next week in particular can get really gnarly really quick, okay? The p hats will become less spread out. So of these things that we have written right now, what will change? What describes how spread out it is? The standard deviation, right? The standard deviation is going to change. Is everybody good? How is it going to change?
Smaller.
It's going to get smaller. How smaller is it going to get? Does anybody want to hazard a guess?
9 times smaller.
9 times smaller? So if that's the case, we could throw a 9,000 in and we should get roughly 0.001.
What's the square root? So 10 times?
So, and when we plug this in, we don't get 9 times smaller, or 1/9, right? It is 1/3. Because that multiplying by 9 happened underneath the square root. We good? So we actually get something like that.
Yeah.
Everybody good? Okay. Let's look at another kind of example. Different wording, but similar ideas. Okay. Polling organization asks a sample of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students are within 50 miles of home. Okay. You guys, tell me something I know. P equals 0.35. N equals 1,500. Will it be normal? How do I decide? NP. It's not, you gotta check them both. Check both NP and N1 minus P. So will it be approximately normal? Those are big. Okay. What are the mean of the p hats? That one's easy. The standard deviation? Just fill in. What are we getting? Yeah? Something like that. Let's turn the page. All right. So if you're this polling organization, isn't it your goal that you want your sample to be at least close to what you're trying to estimate? Okay? So the question becomes, we know that of all the possible samples, of all those p hats, they have a mean of 0.35. We know that the standard deviation of those p hats is 0.012. And I want to know, what is the probability that my sample is going to be close enough, which I'm defining as within 2 percentage points of what the actual value is. Is everybody with me? What would it mean to be within 2 percentage points of the actual value? Two above or two below? Two below is 33%. Yeah? Two above is 37%. You're essentially adding 0.02 and subtracting 0.02. And after that, this is just a normal CDF question. So if those conditions are met that we can call the p hats normal, all of a sudden knowing the normal distribution can be quite helpful. Because it was given to you. I could just as easily had said, hey, it's important to the polling organization that they're within 3 percentage points of the true value. What's the probability that happens? Okay. Like, that's usually some sort of standard that's already put together. And if I'm remembering correctly, it's about 0.896-ish.
That's it.
That could just be like yeah, it's the same idea. When I did this the first time, I used 0.0123. That's why I did it from memory. So that would be a totally, if you got 0.904, that's fine. Because that just depends on where you rounded your standard deviation. All right, last question. What is the probability to get a sample of less than 500 students? You guys, is this describing p hat? This is describing number of successes, right? This is saying what is the probability that X is less than 500? I want us to start getting very comfortable saying, well, that means that's the probability that P hat is less than 500 out of the original 1,500. Now we know that the P hat, now I can do this. By the way, that's probability that P hat is less than 0.33. And we should get approximately 5%.